Hello, class. Welcome to the channel and very welcome to this playlist in which we are discussing different type of faults which can take place in power system. So in this playlist, up until now, we have seen symmetrical faults, we have seen symmetrical components, and from today onwards, we are going to discuss about the unsymmetrical faults. But to understand the concept of unsymmetrical fault, you must have some idea about symmetrical components: positive sequence component, negative sequence component, and zeroth sequence component. So, before we start today's class, if you don't have idea about positive sequence component, negative sequence component, and zeroth sequence component, please click on the I button which is flashing on the top right hand side corner of your screen, and you can check out the video about all three types of networks: positive sequence, negative sequence, and zeroth sequence. And after seeing that, you can jump on to this video in which we are going to discuss about uh, basic unsymmetrical faults like line to line fault, line to ground fault, double line to ground fault, such faults. Okay, so let's start today's class. So firstly, uh, it is very basic thing to start with unsymmetrical components, but you need knowledge of symmetric components: zeroth sequence, positive sequence, and negative sequence. And now we are going to discuss about different types of unsymmetrical faults which can take place in power system. So you can divide unsymmetrical faults in two categories. You can call them shunt faults and series faults. So there are basically three general type of faults which takes place in shunt fault category. First is single line to ground fault. Second is line to ground fault, and third one is called double line to ground fault. Uh, the all three faults are very common, and you will find it. You must have heard it about. You must have heard about it somewhere. And series faults are only the open conductor faults when one or two conductors will left open, and because of that your circuit will not be completed. So these three-phase short circuit faults are very rare, but they have very severe effects on your system, right? uh, all all three type of faults: line to line, line to ground, double line to ground, all of these type of faults are very rare. But when not these three, but short circuit faults, whenever they occur, they leave a severe problems. Okay, these type of faults are very common. The ones we discussed about earlier were very rare. Okay, so these faults are analyzed to find the rupturing capacity of your circuit breaker. And the unsymmetrical fault which we discussed about here are very frequent in power system. Okay, they are not rare. The ones we previously saw are very rare. The three phase short circuit faults, they are rare, very rare. Such faults are very frequent, and sometimes it is possible that in some situation the fault current of line to ground fault is uh, it can it can surpass the three phase fault as well. And these faults are analyzed for deciding relay settings, basically the study of your power system. To understand your power system better, you can analyze such faults, right? And relay plays very important role here. So the method of symmetrical component is used to analyze unsymmetrical faults, and now we are going to watch them in detail. So let's start with the first one, which is called single line to ground fault. So it is very basic type of fault. You can see the figure on the left hand side. So we have three phases: IA, IB, and IC. A, B, and C, three phases. The current in each phase are IA, IB, and IC, and there is a fault taking place in the A phase. Okay, So what you can see here, that there is a solidly grounded unloaded generator. Okay, you can see EA, EB and EC, which means this is a generator. And we are having a fault on A phase. So we will call this point F, which is also happens to be my fault point. And let's try to find what will be the current and voltage of what will be the current and voltage when such fault will occur in my whole system. So voltage of this phase VA will be 0 whenever my line to ground fault occurs, which means my line is basically grounded, right? And as my system was already grounded and line is also grounded, there is trouble. Now when my line will get grounded, what will happen? There will be no flow of current in this phase or this phase, right? So IB and IC will become 0. And when we try to find the symmetrical components, IA, IA1, IA2 and IA0, we will call it IA1 for positive sequence, IA2 for negative and IA0 for zeroth. So we know this matrix A, which we call it, in order to find the symmetrical component. So you can find it using this formula. IA1 is equals to 1 by 3 A into your I matrix. The A is given by this matrix: 1 alpha alpha square, 1 alpha square alpha and 1 1 1. So how the formula will look like? It will look like that. And when you calculate values of IA1, IA2 and IA0, you will get 1 by 3 into IA, because value of IB and IC are 0, and whenever you take the multiplication, because they are 0, this alpha and alpha square component will become 0, and only thing you will have is IA. Only IA you will have. So IA1, IA2 and IA3 will be equal, and what value will it hold? It will hold 1 by 3 IA. Now to search this sequence network equation for all three symmetrical components, VA0, VA1 and VA2. So previously we have derived these equations. So VA0 will be minus IA0 Z0 plus 3ZN. VA1 is EA minus IA1 Z1. VA2 will be minus IA into Z2. Okay. Now uh, there will be some voltage across the fault, right? So this faulty phase voltage we will give using uh, we can write this phase voltage in terms of symmetric components as well. So what is the value of my fault voltage? It is we where there is a fault occurring in A phase, so we will call this voltage VA, which will be equal to IA into ZF. And we can write IA using this formula, right? Because it will get divided in your positive, negative and zeroth sequence. So VA1 plus VA2 plus VA0 is equals to 3 into IA1 into ZF. Now what we will do, we will simply substitute the values of VA0, VA1 and VA2 from earlier equations. From these equations we have already derived the values of VA0, VA1 and VA2. So when we do that, what we will get? We will get an equation, this equation, right? The value of VA1, EA minus IA1 Z1, VA2 is minus IA2 Z2, and VA3, VA0 is equals to minus IA0 Z0 plus 3 Zn. Right hand side will remain as it is, and what you will do, you will make IA1 subject, so you will find the value of fault current. Now that you have found the value of fault current, now I want you to look two equations very closely. The equation of fault current itself, which is E divided by Z1 plus Z2 plus Z0 plus 3Zn plus 3Zf. Basically my ZF is the fault impedance, you can call it, impedance of point where fault is occurring. So I wanted to look this equation 6.2.6 and the earlier equation, the second this one, the equation of VA0. Can you tell something from it? They are indicating something to you. What does these equations have in common? They are indicating that the for analysis of this line to ground fault, all three sequence networks are required in your calculation, right? You can simply see it from this equation. Even if you see this equation, right, ia1, ia2 and ia0, all of them are holding same value. So you need all three components for this calculation. And how will you do this calculation? So firstly, know that all the components of my current sequence current components, let's call them, so all of them are equal in magnitude and phase angle. So there is a balance between them, and that's why we are talking about unsymmetrical fault analysis. There is no unbalance in phase. The and then this three sequence network, you must connect this network in series. Okay, and we will come to how we connect that later on when we discuss about it. We will later on come to that, how do we connect the connect all these impedances in series. But after that we also have to calculate the value of ia1, ia2, ia0. All three of them are same, so you just calculate one and rest of two will be equal to that. And then we have to calculate va0, va1, va2, right? So okay, not after that, but we have to calculate value of va0, va1 and va2. So let's try to find the value of va1, va0, va2. You can give this equation. So va0, va1 and va2 is equals to, you will put the value of voltages which we have came across, which we have found, right? So 0 for va0 and va2, and 1 for ea for va1, minus you will take the self impedances z0, z1 and z2, and you will consider all three type of currents: positive, negative and zero sequence, which means ia1, ia2 and ia0, which you can see here. Now what we will do, because we know the all three currents are having same values, zero sequence, positive sequence and negative sequence currents are having same values. So can't we write ia1 instead of ia0 and ia2? So we will write it simply here, right? And now we will take the multiplication of these two matrices, and what we will get these values: ia1 into z0, ia2 ia1 into z1 and ia into z2, ia1 into z2. Basically current is same, so impedance will get multiplied with same currents. And now when you take the subtraction of these two matrices, there will be no change, except your matrix will get negative sign over here, and the second component will become ea minus this term. And when you represent it separately, or whenever you take addition of all three components of them and you compare it with 0, then what you will get: va0 plus va1 plus va2 is equals to minus ia1 z0 plus ea minus ia1 z1 minus ia1 z2, which will equal to 0. And from that equation only, it will be very easy for you to find the value of ia1, because Here you can take IA1 in common and you put all the rest of the term in the division of this term, and basically we initially we took VA0 plus VA1 plus VA2 is equals to 0. So what you can do here is you only consider this term, the second term, right? And you will equate it with 0. And what you will do, because IA will be common from these terms, but EA will not be common from these terms. So what you will do, you will put EA on the other side, and you will take whatever you have in multiplied with I and put it into the denominator of EA. So what you will get, you will get the value of IA, and that IA will be your current of phase A, the positive sequence of current in phase A. And as we know, all three of them are IA1, IA2 and IA3. You need to take summation of all three of them in line to ground fault for like you have to take summation in order to find the value of neutral current. Okay, so what you can do, you can take the summation of all three of them and you can find the value of neutral current. And because we know that IA1, IA2 and IA3, all three of them are holding same values, so what you can write, 3 into IA1 you can write. So you will simply write it. Now is if this neutral will not be grounded, then the zero sequence impedance Z0 will become infinite. And whenever such thing happens, because my impedance is infinite, then the current flowing through that impedance will be how much? It will be 0, right? And because of that, your IA1 will be 0, because there is infinite impedance, and because there is infinite impedance, current will not be flowing through it. So simply the value of IA1 in such case will become 0. And earlier, remember the circuit I was telling you about. So here is that circuit which I was telling you about. By the way, you can obtain the same result if the system is isolated from neutral. So because there is no return path for my current, and because of that the value of all three symmetrical components will be 0. So what does it indicate? So it indicates that for this system, the symmetrical fault or the fault current will be IA, and that will be 0 if my zero sequence impedance becomes infinite. Okay, so here we have the figure I was telling you about. You are getting a voltage source, you are getting all three values of your three components, positive, negative, zeroth. You can see Z1, Z2 and Z0 plus 3 Zn. You got all three of your components, IA1, IA2, IA0 you got. And here is your fault impedance, 3ZF. So this will be the circuit for single line to ground fault, or LG fault, normally known as LG fault. Let's move towards the second one. The second one is called line to line fault, and this fault is also very common fault. It occurs every now and then, especially in rural areas. So one more time, see this figure, see this second figure, and you can see that from this figure, this one is also an unloaded generator having three phase, and this time the fault is taking place between two lines. These two lines are B and C. So because the fault is taking place between two lines, the this type of fault is called line to line fault. So now let's consider that a line to line fault is occurring between terminals B and C, as you can see in this image, and the fault impedance is ZF C. So let's try to see what will be the value of the current and voltages after the occurrence of my fault. So because fault is occurring between phase B and phase C, all the current will be flowing through these two phases. Actually, the fault current or the current which will be flowing through B phase will be exactly same as the current which will be flowing through the C phase, but with reverse direction, which means IC will be equal to minus IB. Now there is fault occurrence of fault between these two phases only. That means there will be no flow of current from my A phase. Yes, there will be no flow of current in the phase A. And when you take the potential difference between phase B and C, which means VB minus VC, it is very much clear from this picture only, right? What will be the value of phase potential between phase B and phase C? It will be IB into ZF. Very much clear. So now again, this time try to find the symmetrical components for this one. So when you try to find symmetrical components, see, again we will apply the same formula we applied by the time when we were doing the calculations for line to ground faults. So we will apply the same formula, and this time the change is the IA will be 0, IB will remain IB, and IC, remember I told you it is flowing in the reverse direction, same magnitude, which means IC will be equal to minus IB. So the formulas this time we will get will look like this for all three current components of positive, negative and zero sequence. Zero sequence current will be 0. Positive and negative sequence components we will find. The value of positive sequence component or IA1 will be 1/3 alpha into IB minus alpha square IB. You are basically taking the multiplication. Okay, alpha into IB minus alpha square into IB. Same we will do with IA2, which means 1 plus 1 into 0 0 alpha square IB minus alpha into IB, right? And zero sequence will be, you multiply this with this will be 0. 1 into IB is equals to IB, and 1 into IB is equals to IB, but this one is holding minus sign, so IB minus IB will become 0. So zero sequence component is 0. Now when you try to find the value of voltages here, the symmetrical component of voltages at my fault point F, we are calling the fault point F. So what will be the value? So here again see the VA1, VA2 and VA0, positive, negative and zero sequence of my voltages. We know there will be some value of VA and VB, but what will be the value of VC? So it will be VB minus IB into ZF, the potential difference between these two. So it will be, you're trying to find the value of VC, right? So what will it be? Make VC subject here, so it will be VB minus IB into ZF. Very much clear. And based on this formula, you will try to find the value of VA1 and VA2 and VA0. VA0 basically you will not require, so we have not bothered with its value. So we will take value of VA1 and VA2. Basically the 3 came because it was divided over here, so we simply took it on the left hand side and multiplied it with VA. Okay, so you can keep it in the denominator if you want, there is no issue doing that as well. And value you will be getting will be 1 into VA is equals to VA alpha into VB, so plus VB alpha plus alpha square into this whole term, which means alpha square will get multiplied with whole term. Same ways you will be deriving the value of VA2. 1 into VA will remain VA, alpha square into VB will become alpha square VB, and alpha into this term will become whole term getting multiplied with alpha. Now from these two equations, now I'm telling you we need to take the subtraction of these two equations, which means I want to subtract this equation of 3 into VA1 from this equation 3 into AV2. So when we will take subtraction, this va will get cancelled, right? And just like that, this alpha into vb and alpha into vb will also get cancelled because I'm taking subtraction. So the signs which are same signs will get cancelled. This look at this, alpha square vb and alpha square vb also holding same sign, it will also get cancelled. Only thing we will be remaining will be this alpha square ib into zf minus alpha ib zf. So we will take alpha common, alpha minus alpha, sorry, we will take ib into zf common, so we will be left with alpha minus alpha square. So the final value will be the value of alpha minus alpha square is basically root 3j, right? So what you will get, you will get root 3j is zb into ib, zf into ib, and based on that you can find the value of ia, ib and ic, just like we did for voltages. And remember, this time we are finding the value of we are finding phase values from symmetrical components here, which means this time we will not be taking the matrix A, but instead of matrix A we will be taking A inverse. So keep in mind, this matrix is not same as this one. This is actually the inverse of this matrix. Okay, this matrix is called A matrix and this is called A inverse. So we will try to find the value of IA, IB and IC, which means the phase value of my current from this one. And when we take the multiplication, because this time you already know what will be the value of IA, because we initially considered that value of IA will be 0. IB and IC both are equal, but magnitude is both are equal in magnitude, but direction are opposite, which means IC will be equal to minus IB. So you can write it instead of it. You can write it this way. Right, you can write it this way. And also you know value of IA1, IA2, IA0. You have derived it over here, you can see. So you can also substitute those values. You know IA0 holds no value, which means it is 0. So we will substitute it. IA1 and IA2 both because see, this one is basically the same equation, but we are writing alpha square minus IB ahead of it, which means this is basically minus IA1. So you can write, instead of a whole term, you can write IA1 and minus IA1 here. And based on that we will be finding the value of IB. And whenever we do the math and calculate the value for IB, what you will get, you will get uh, alpha square into IA minus alpha into IA, alpha square into IA minus alpha into IA. That will be value of your IB. Now I've already told you what is the value of this time we will take IA1 common and we will be left with alpha square minus alpha. And I already told you what is the value of alpha square minus alpha, minus j into root 3. So we will put it over here, and now there you have it, the value of IB. Now what we will do, we will simply substitute this equation in previous equation, in this equation. So we will be substituting value of IB in this equation, and what we will get, 3 into VA1 minus VA2 equal to value of IB j root 3 into ZF, sorry, j root 3 into ZF was previously here, so value of IB minus j root 3 IA1. Okay. Now you know what is the value of root 3 into root 3, which means root 3 into root 3 is equals to 3. So here we are having 3. ZF will remain as it is, IA will remain as it is. What is the value of j into j? J into j is j square. What is the value of j square? It is minus 1. But we are already having a minus here, which means minus minus will become plus. So you will be having 3 ZF into IA1. And this 3 will get cancelled, I don't have to mention it. So you will be left with 3, you will be left with VA1 minus VA2 is equals to 3 ZF into IA. So you know that these equations same as we concluded as with line to ground fault. This equation, see this equation and see the previous equation. This equation, again both of these equations are indicating something to you. What is it saying? So it is saying that uh, the positive and negative sequence are required to be connected in parallel connection through series impedance ZF, which we did in this network. You can see you are connecting both of them in parallel, and the series impedance is also, you can see, it is ZF. So if the value of zeroth component IA0 will become 0, which means the zero sequence network is not connected at all, then what we can do, we can find the value of VA1 and VA2 simply, the positive and negative sequence voltages from the initially derived equations. Like where did they go? Wait a minute. Initially derived equations, which are basically my this equation. Okay, VB minus VC is equals to IB ZF. So from that we can find the value of VA1 and VA2 as well, because you know VA1 VA2 from these equations, VA1 and VA2 from these equations you can find the value as well. And when you do so, you will find this formula: EA minus IA1 Z1 is equals to minus IA2 Z2 plus IA2 ZF. Here again you will take IA1 common, Z2 plus ZF will be there, and you will make IA1 subject, and you will be able to find the positive sequence current or positive sequence fault current, right? So you now you know the value of IA1, VA1 and VA2, which means you can easily from this voltage and currents you can easily calculate the fault current and do the proceedings. So this was your line to line fault, and I will quickly talk about the double line to ground fault or LLG fault. Again same, see this figure, it is again unloaded generator, and you are seeing a double line to ground fault. Both of these lines are getting short circuited and both of these lines are getting grounded. So and these lines are B and C, as you can see. So what we have to do, we have to calculate the current and voltages at my fault point again. So you can see I have mentioned it here. The current is 0, IA will be 0 whenever there is a short circuit between two lines and both of the lines are grounded. So there will be no flow of current in this phase. So no phase current for A phase. Again all three of my components are balanced, so IA1 plus IA2 plus IA0 will be still equal to 0. But let's try to find the voltage between these two phases, VB. So VB and VC will be equal basically, because both of them are got shorted. So it will be ZF into, see what will be the current. ZF is my impedance, fault impedance. Two currents are coming from different phases, so IB plus IC will be the value of my VB or VC, whatever you want to call, because both of them got shorted. Now let's try to find the positive, negative and zeroth sequence component for all three of them. So we'll implement the same formula, and this time we can write, instead of VB and VC, because both of them are equal, you can write either of them. So we are mentioning VB instead of VC. The matrix A will remain as it is, rest of things as it is, and you will be finding value of VA1, VA2 and VA0. So we can find the value of all three components. So you can see what will be the value of VA1. 1/3 will remain as it is, 1 into VA, alpha into VB and alpha square into VB again. So what you will get VA plus alpha VB plus alpha square VB. Same ways we can find the value for VA2 as well. It will be same as well, VA plus alpha square VB plus alpha VB. But the value of VA0 will be one third VA plus VB plus VB, which means one third VA plus 2 VB. So now you have values of VA1, VA2 and VA0. Uh, and also see here VA1 and VA2 are equal, right? There is no difference between them, just the terms are getting rearranged. So basically both of them are equal. Now you have values of VA1, VA2, VA0. You can simply uh, subtract these values because VA1 and VA2 are equal and VA0 is different, so you can subtract VA1 from VA0. And let's see what we will have this time, because we did the same previously as well. So when you do so, you will get VA0 minus VA1 is equals to one third. This VA will get cancelled. You will have 2 minus this 2 minus alpha square, because VB is common in all three of them. So 2 minus alpha square into VB. Okay, and remember again, I've told you what will be the value of alpha minus alpha square. So in the end, when you complete your math, you subtract that value from 2 and divide it by 3. You will be left with 3 into, basically you will be left with VB, because this term will be 1 eventually. So 3 by 3 will be 1 and you will be left with only VB. So what you will be left with VB, and what is the value of VB? So come here and see, the value of VB is equals to 3 into ZF into IA0. So value of VB equal to 3 into ZF into IA0, and you will be finding the value of VA0. So in order to find the value of VA0, what you can do, you can simply send VA1 on the other side. So you will get VA1 is equals to VA0 equals to VA1 plus 3 into ZF IA0. So it's that simple. You can simply find the value of all three components, and from these equations, the equation of my VA0, zeroth component voltage, equation of my first component, positive component voltage, and the fact that the system is completely balanced, so there is a same flow of all three sequence of currents, IA0, IA1 and IA2. You can draw a circuit diagram, and when you do so, it will look something like this. Wait a minute. So it will look something like this. You can see we can write the equation for current using Thevenin's theorem or Thevenin's equivalent circuit, and when you do so, your IA1 component will look something like this. I'm not doing the math. You can do it, you can perform it using this circuit and the knowledge of circuit and networks. So and again, as you can see, you have all three components here, Z1, Z2 and Z3. You can see the currents IA1, IA2 and IA0 again, and we have connected IA2 and IA0 with 3ZF, which is my fault current, because it was double line to ground fault, which means my fault was occurring with second and third line, or B and C phase. So we have connected the fault impedance between them, and remaining things are pretty much self-explanatory, right? Like this this EMF here. So we will keep this lecture till here. In the next lecture, we will discuss unsymmetrical faults on power systems in detail, like same faults, but in little bit more detailed, and in using Thevenin's networks as well. So if you have any doubts, any queries, or any suggestions related to this class or this playlist, please feel free to mention them in the comment section below. They are very valuable to me, and I will try to answer them as soon as possible and as much as possible. So I will be seeing you in the next class. Till then, thank you very much for listening and take care of yourselves. Goodbye, everyone.